Hi everyone, how's everyone doing today? I hope just as good as me. I'm doing okay today. I'm going to be moving right along. I'm going to be discussing again what we discussed the other day. I'm going to continue with what we were doing. In other words, I'm going to be analyzing the debate I had with this fellow named Peter. No name, no last name, just Peter. Um, he's a mathematical physicist. He came over to question, challenge the rope model, and I kind of steered him over a little bit into what physics is about. In other words, the foundations of physics. And I think we need to get the foundation straight first before we can do any higher level physics. We need to uh, double check our kindergarten stuff before we go to college. Okay, and the problem right now is kindergarten stuff. Mathematical physics doesn't meet the minimum um, criteria, the minimum spec for what is physics. And that's the issue. That's the issue that I'm trying to make people aware of. We have to go back and find out what is physics, and even before that, what is science. And what I'm saying is essentially, in a nutshell, that for the last 400 years, the mathematicians have taken over, just developed this way. It's not a conspiracy or anything like that, just the way things evolved. And it turns out that the inheritors of science, of physics, have been the mathematicians. And so they self-servingly converted uh, physics into math and math into physics, science into math and math into science. And that's the issue. The issue is that um, we're not doing science anymore. And you're saying, well, is that right? I mean, haven't done science. Look at the progress we've made. Look at all the technology we have. Science can't be that wrong. And yeah, science is wrong because we're not talking about technology. Technology is fine, and we developed that by trial and error, so it's got nothing to do with science. Science is about explaining a phenomenon rationally, and we don't have that today. We don't have a single rational explanation from the mathematical establishment for all those phenomena which are mediated by invisible entities: light, gravity, magnetism, the workings of the atom, electricity. None of those can be explained today. They cannot give you an explanation where they use objects specifically, where you can visualize what's going on. And so that's when they go back to spirits. We're back to the Dark Ages. They do it with spirits, and they call these spirits with different names, and they all have these scientific sounding names, but they're spirits. Make no, no qualms about it. It's spirits. Okay, so what were the problems that I found with Mr. Peter? He went by the name of Peter. Uh, the first one is that anonymity. I covered that, and the second one there, didn't understand the golden principle of physics. And that's about as much as I got to cover the other day. Let me just say the following. As far as anonymity is concerned, all it shows is that there is an environment of fear. There's no reason for Peter to remain in hiding, in secret. Uh, what would be the reason for him to avoid, coming out and saying, look, I'm Peter, and I'm a physicist, and I challenge the rope model. Fine. But he didn't do that. He kind of didn't want to be known out there. Maybe his colleagues might think terribly of him if he's debating someone who disagrees with mathematical physics, doesn't agree with the foundations of quantum mechanics or relativity or string theory. And and yeah, people are afraid for their jobs, and so I think that's the main reason. He didn't want to be embarrassed in front of his colleagues or whatever. Who knows? But I think there's an environment of fear, and it also shows in what is published, what is allowed to be published, and what is allowed to reach the public. And what you will not see reaching the public are oppositions to quantum or relativity. And so they constantly claim, it's never been falsified. You read that everywhere. You read it in papers, you read it in the Wikipedia, you read it all over the place that, quantum has never been falsified. Relativity has never been falsified. And people say, oh, so they're sound theories. Well, yeah, they've never been falsified because you're not allowed to criticize these theories, if you can call them that. You're not allowed to criticize them from a qualitative point of view. You cannot say that they're irrational. In fact, they'll beat you to it. They'll say, oh, we know it's irrational. Nobody understands it. So how can you say that it's been proven? How can you say that these theories, are ground in stone? And they're not referring to the physical interpretation. They only look at the quantitative stuff, and they also look at what they observed, or so-called observed, in the lab. So they see something in the lab, they interpret it for you, making assumptions, specifically the assumptions that everything is mediated by particles, and that's all you'll ever hear. And they won't allow you to come up with an alternative to that. And yeah, that creates some problems out there, because when you try to challenge it from a rational point of view, they agree with you. And they say, yeah, we don't care about that. We know we can't understand it. We've proven it, but we can't understand it. So all they're saying is, we saw something in the lab, we interpret it in terms of particles. It doesn't make sense to us, but look at the equations and look at the technology we've developed. That's the argument. That's the argument they have. There is no other argument. Okay, so what are the problems with Peter? Well, Peter sent some 4 articles to me. These were the 4 articles. The first one had to do with the slit experiment. The slit experiment, because essentially it's Tanamura's, he's a Japanese researcher, and Tanamura and his group did the slit experiment with electrons and electricity, essentially, and he claims he handled 1 electron at a time. The second one is a 3-slit experiment with 3 slits. The third one is Compton scattering. And the last one is the electron-positron annihilation experiments done by an organization known as LEP. Okay, these were the papers that he sent me. He's saying they debunk, or in his opinion, I have no way of explaining that with a rope model. Okay, so that was his argument, the way he came into the debate. And the problem with the 4 papers is that, none of them had objects in them. In fact, you won't see a single picture of any object that mediates any of the phenomena that these people analyze there. So what is the problem? The problem is that we have no objects. And let's go with the first one. Here's Tanamura. I'm just going to go briefly through them because I've covered that in the previous lecture. But let's go quickly through them. What's wrong with them? Here's Tanamura's single electron, how he handled each one. But the problem is, he says, look at that second line, the relative phase shift was measured between 2 electron waves. 2 electron waves. And then later on he says, when the magnetic field was confined. Right at the bottom there. The magnetic field was confined. So he confined it on a magnetic field, and he talked about passing electron waves through, I guess, the slits, right? Well, we got a problem with that first because Tanamura wrote a paper a long time ago. Let's see if I can see it here. Give me a second here. And he wrote a paper, what is it, 1989. The one at the bottom says Tanamura there, his group, demonstration of single electron buildup. Okay, so Tanamura's been doing slit experiment for quite a while. He's doing it with electrons, And in this case, he did it with single electron, but in his current paper, the one was sent by Peter, he talks about passing electron waves. Well, yeah, it's this old duality between wave and particle. Is an electron a wave or is it a particle? Well, they tell you it's both. Whenever it's convenient for the mathematician, they convert the particle into a wave, and whenever they want to explain another aspect of their experiment, they'll convert it back into a particle. And that's the problem. The problem is that, the electron is this malleable ghost. Turns into a leprechaun when he hides his gold. When you go and try to catch him, he turns into a spirit. He fizzles out of your hands. And that's how the electron works. And you say, well, that's irrational. How can the electron spontaneously and for no reason whatsoever, and by what mechanism, convert from a particle to a wave and wave to a particle? Wave is an elongated, spread out kind of thing, and the particle is like a concentrated point. It's a condensed piece of matter there, a little dot. And, these are two conflicting notions of what a thing is supposed to be. Is the electron a ball, tiny ball, or is it is it an ocean, bunch of waves? Which is it? And they say it's both. And that's the problem. The problem is that until we can figure out, what an electron looks like, we can't say that, an electron hit the wall. Because again, Peter suggested that, it's like we noticed that there was something happening at the wall, like a single hit, and what else could it be? And I showed what else it could be the other day. I'm going to get into that in a minute, but let's continue here. Maybe I should show that. Give me a second here so I can find this right here at the bottom. Here's the way these folks do it, quantum. They do it with cannons. They throw cannonballs at the walls to make holes in them. This is their notion of how an electron is shot and how an electron hits the wall and makes a hole. Okay, so holes are made with cannons and cannonballs. These people are still in the 19th century. Well, how do we do it in the 21st century? Well, we do it a little differently. We do it with, here it is, with a drill bit. We drill holes. We don't shoot cannonballs at the wall. We do it with a drill bit. And the drill bit, twirls around and makes a hole in the wall. It never occurred to them that electricity could be a drill bit, like a drill bit. And here is electricity, as I always point out. Let me make that a little bigger so you can see it. Electricity is a whole bunch of electron shells. And here's a simple picture of it. In other words, here we're using hydrogen atoms. The simplest s orbital, that's it. Obviously, it's a lot more complicated than this, but here we can see the essence of it. All these shells are interconnected. They form what I call a serpentine. That serpentine twirls in place. And what you have is electricity going into your face there. And what's going at 90 degrees is the field, the magnetic field, which is at 90 degrees to electricity, which is what's going in your direction. And so this is a new notion. We're saying that's what electricity is. And obviously that fits in with the drill bit twirling in place. That's what we're saying. That's how the holes are being made. You need to have atoms in order to have electricity. Without atoms, there is no electricity. There is no electricity in empty space going from one galaxy to another, like the electric universe, for example, maintains. You need atoms to do that. And the problem is that all these people, the quantum people and the electric universe people, which is just a sect of quantum, they believe that, electricity consists of a bunch of beads that travel through space, like a flow of beads. And so if anything, in a vacuum, electricity should travel much easier because the mean free path is increased. I mean, if you remove all the matter, just think of this. You're going to remove every atom, okay? And so now there's no obstacle. So now all these beads, all these electron beads taken out of their atoms, right? And we've got all these electron beads. We removed them. We've ionized every atom. Now we've got all these loose beads. They form a flow of beads, right? They're moving along. And you shoot them with a gun or whatever, like Dr. Quantum did. I'm going to show that in a second also. He throws them, at something, at a wall. And there's no atoms in between the gun and the wall. No atoms whatsoever. So there's no obstacle. These electron beads should flow like honey. They should, no problem. There's nothing stopping them. And that's not the case. That's not the case. You need atoms to have a flow of electricity. And they never learned this. The more you pump down a chamber, pump it down to minus 7 torr, minus 8 torr, minus 12 torr. You have minus 11 on the moon. They also measured minus 11 range in outer space, in interplanetary space. They had I think it was Apollo 14 or 15. They, in the back, they opened up the the trunk, and they had a little machine that read the vacuum level of space as the Apollo was going to the moon. So in the middle of space between the Earth and the moon, they measured the vacuum, and it was in the minus 11 range. And that's what they also measured on the moon. So we're pretty comfortable that in interplanetary space, when you don't get too close to a planet, like, Jupiter's got a lot of gases and so on, when you don't get too close, like you're talking about between two planets, you're going to have maybe minus 11, minus 12 range, minus 11, minus 12 torr, okay, just because there are different measures, there's pascals and so on. I'm talking about torr. So, you're going to have minus 11, minus 12 torr. That's high vacuum, very high vacuum. There is no electricity in minus 11 torr. And even though there's gazillions of particles in there, I mean, you have like 300,000 particles, I think, per cubic meter. So there's still a whole bunch of particles there in a minus 11. So keep that in mind. There's still a whole bunch of particles in there. I'm not sure how many thousands. I'd have to look it up. But I know there are thousands of particles per cubic meter. Even so, in that low density region, you cannot have very much current. And in fact, Peter, he suggested that in a high vacuum, I think they worked in a minus 7 range, they could shoot like 1 electron every 20 seconds. Yeah, I don't doubt that. I mean, I don't think you can have a current with high vacuum. You want to have current, you need to put something in there. In fact, at AMD, we used to put, we pump the chamber down to minus 7, then fill it with argon, ionize the argon, and use the argon ion as bullets. And we shot them against an aluminum target or titanium nitride, depending on what we were sputtering. And it acts like a machine gun. All these ions just hit the target and chip off pieces which fall on the wafer. And they give you a nice coating of the wafer. But you need to have something in there in order to have electricity. Okay, and they never figured that out. They think it's a question of shooting bullets through the vacuum, and that's not the case. And so, yeah, it's a different way of doing electricity. It's a drill bit. Anyways, Tanimura had that problem. The other problem Tanimura had is that he mentions the word field, and this is a field. That's what a field is. You got 3 types of field here. You got an electric field, magnetic field, and gravitational field. And the ones on the bottom are the same things, but without that little dot in the center, without some matter, because that's what quantum claims that a field is, that you can have a field without matter, without an object. Okay, so the ones on the bottom have no objects in them. And so you say, well, what are those arrows? Well, those are, these are vectors. That's all they are. They have magnitude and direction. So you have a bunch of magnitudes and directions, and that's a field. In fact, we don't have to kill our brains here. We'll let a mathematical physicist tell you what a field is. Here we have Mr. Sean Carroll. He gave a presentation in, I think it was in Cambridge. Particle at the End of the Universe, 2013. He says, instead of thinking about random forces between objects very, very far away, imagine there's a field filling the universe. Ooh. And what that means mathematically is that at every point in space, there's a number. There you have a definition of a field, what he means by field. At every point in space, there's a number. The value of the field, just like the temperature of the air in this room. At every point, there is a value of the temperature at that point of the air. Look at the bottom down, last paragraph. The field is what the world is made of. Particles are what you see. So the atom in this table, the electrons, the quarks, the protons, these are all vibrations in fields. There's a quark field that is vibrating, and you look at it and you see quarks. There's an electron field that is vibrating. There's a neutrino field that is vibrating. There's a gravitational field that is vibrating, and so on and so on. Okay, so he defines it as every point in space there's a number, and now he's saying that these numbers are vibrating. In other words, the field, the entire field is vibrating, and that's what a particle is. So we associate particle with the vibration of the field. Well, here, you'll see it for the first time in your life. Keep in mind, you can say that you saw it here first, okay? And here it is. Here's the field. You ever wanted to see a field? Here I have a field for you. That's a field. Bunch of vibrating numbers, values, quantities, amounts. And as you can see, the numbers get bigger towards the center. And as you get away from the center, the numbers get smaller. That's a field. And they're vibrating, so what you're staring at is a particle. The particle is a vibration of the field. And what is a field? A bunch of numbers. So this is what these people are saying. And this is not a semantic issue. No, it's not. It goes to the heart of what these people are saying. They're saying a particle is a vibration of a field. And what is a field? It's a bunch of numbers. So there you have it. That's exactly what they're saying. So this is not semantics. This is what they're saying is their field, and what they're saying is their particle. So whenever they talk about particles, you have no idea what they're talking about, because they're not talking about a corpuscle. Okay, they're talking about a vibrating field. Okay, so Tanimura fails on all counts. Tanimura says, look, first we're dealing with fields. What's a field? Field is just a bunch of numbers. Second, we're dealing with waves. But the wave is what passes through the slits. What we detect is a cannonball, on the wall, on the screen, or wherever or at the detector, wherever he senses this, right? So, how much weight should you put on Tanimura's paper? None. Absolutely none, because it's on an unscientific paper. And again, they won't allow people like me to review his paper and show him that, where all his errors are. It's reviewed by his colleagues, people who give each other Nobel Prizes, and so they all are in the same club, and they all vouch for each other. And they're the ones who control the reins of editing, of editorial space for the big magazines, the big journals. And someone in a popularization magazine, who usually is also a mathematician, he translates that for the public. And that's the way it works today. So you will not see criticism of quantum or relativity out there in the mainstream. Okay, the second paper was about superposition, and this is what that's about. Paper said exotic loop trajectories of photons in three-slit interference. What's the problem here? The problem is, first, the fact that they're talking about predictions. I talked a little bit about that the other day. They're predicting the past. But whenever they use the word prediction, they really mean explanation. Okay, that's what they're saying. And but the point here was that they're talking about observing. What do they observe or measure? They measure excitations of plasmas and of fields, near fields, in the vicinity of slits through the excitations of surface plasmons. We just covered the field. What's a plasmon? Look at the bottom. It says a plasmon is an amount, a quantity of plasma oscillation. And what's a plasma oscillation? Rapid oscillations of the electron density. What's an electron? It's a field, it's a vibrating field. So we got all these circular arguments where it's just one concept underlying another concept. There is no physical object in all of quantumdom, let alone, well, in all of mathematical physics. Okay, and so here is their, this is what they put in quantum optics, which is more or less a publication for the public. Okay, and the issue here was that the first two lines there that are underlined, you see prize on offer disproving the principle of superposition, with which they would destroy quantum mechanics. What they're saying here is, and that's in the next line there, to investigate whether superposition really occurs in nature. Is this what science is about? About just verifying that superposition occurs in nature? And if it does that prove quantum mechanics? Is that the issue? I mean, what they need to do is explain superposition. If they're just going to go out there and say, look, you know, we verified one more time that superposition occurs, does that ratify quantum mechanics? No, it just ratifies that they're still ignorant. They can't tell you why superposition occurs or by what mechanism occurs. And let me tell you what superposition is here, which is what I did the other day. Here you have Dr. Quantum, and he's going to shoot bullets. And let's see when it starts here again. Give it a second here. We're going to see him crying because he can't figure it out. Okay. And what's the problem? The problem is these folks do everything with particles. He's got his marble machine. He's going to shoot particles through a single slit, and obviously he's going to get a single line. When he shoots through two, you should expect to see two lines, but instead, always with particles, you see many lines. So he tries one particle at a time with his single beam shooter. The problem is here that the particle is at two places at once, and then recombines on the screen. Okay, so what are they saying? They say they have this decoherence and superposition nonsense. They say that a particle can, well, here I have it illustrated, so why explain it when we have it illustrated? A particle can be at two places at once, and it also can have two states. It can be vibrating, and at the same time, it cannot be vibrating. And when you try to check one state, it immediately converts into one or the other. So this is what they have. They have an excited atom and a non-excited atom at the same time, and they have one particle occupying two different locations at the same time. And they call this decoherence and superposition. Okay, so this is where we're at today. This is, and they claim this is science. And so the question is, you know, when you criticize this and say on a qualitative basis, they say, well, we know we can't understand it either. So you're wasting your time. You're attacking a straw man here. What you got to do is go to the lab and verify that superposition and decoherence happen. In other words, their interpretation of it. And second, look at our math and see it's all correct. We've got it all covered with equations. And we do develop technology, so everything is fine. And we never get an interpretation, a physical interpretation, an explanation for what's going on. And they say, well, you know, we don't understand it either. Of course you don't understand it, because if you applied Popper, your own Popper, you know, they do agree with Popper, Karl Popper, and he said that, you know, if an experiment falsifies your theory, you should reject the theory. Well, they didn't. Instead of rejecting quantum mechanics, because all experiments, 150% of them, falsify the particle hypothesis, what they said is, look, whenever, you know, we falsify the particle hypothesis, we just convert it into a wave and we continue rolling. So they have this duality, and they still keep quantum. They're not going to reject quantum. That's what's happening. And of course, you won't find a single wave in the standard model. All you will find is the particles out there. I think there's 13 of them, primary ones. There's over 200 that they've found so far, they've invented so far. And you won't find a wave. And the other thing you won't find is a picture of any of the particles. They've never seen a particle. They're assuming that they're dealing with particles. And so here we have the fourth paper. Where is it? Here it is. Was this the fourth? No, this is the third one. Sorry, I'm falling behind again. This is X-ray Compton scattering. Okay, and what are they talking about here? Again, no objects. All we're talking about single particle excitations. You know, the Beach Boys used to call it good vibrations. These guys call it excitations. Okay, two identical photons convert into a single photon. And what's a photon? It's a vibrating field. So we're done. You know, I mean, we don't have any objects, and I'm not going to go through it in more detail than that. All I'm going to say is here you see what their attitude towards this is, and here's a comment by this physicist, I guess, mathematical physicist. She says, "We know that our present theories are correct to high precision, and new theories cannot differ by much, or they are false already." Okay, and again, they talk about interactions between rays. They claim they observed a process. They observe something that's visible, and they infer what's invisible, and they convert the two photons into a single photon. You can take as much as you want from that. You know, they cannot explain what they did. All they do is describe, and they say, yeah, this is what we observed, and so it confirms quantum mechanics. What does it confirm? You don't have an explanation. It doesn't confirm an explanation. It just confirms that you observe something, you're describing it in terms of particles, and you call that confirmation of quantum because you're confirming your assumption. That's what they're doing. And here's the last one. Where is it? Here. Here's the paper where we have the what is it, the electron and positron annihilation. All they did was do measurements. This report was only about measurements, but these measurements supposedly confirm that there are electrons, there are positrons. A positron is a negative electron. When it meets a negative electron, what happens? Well, at that point, they annihilate. And what's the problem with that? Well, the problem with that, again, is that you're assuming that an electron and a positron are particles. We don't know what they look like or why they are so different, so opposite, and why they, when they combine, they end up annihilating, turning into nothing, I guess, just energy, you know. And so the question is whether they're dealing with particles when they visualize these experiments. In other words, they observe something visible in their chambers, and then they interpret, and they say, well, what we think we saw, what we know we saw were particles. One is the electron, the other one the positron. One has a negative sign on its back, the other one has a positive sign, and when they meet, they annihilate. They turn into nothing, or energy, or whatever. They turn into a concept. And what's the problem with that? Well, the problem comes with Mr. Anderson, Carl Anderson, a long time ago, 1932. He came up with a suppositron. He called it the positron. I call it the suppositron, not because it's a suppository, but because he supposed that he was dealing with particles. And this is what he saw. He saw a little line, that curved line that you see on the left, and he saw that on his chamber. And that line went right through the bar there. That's a lead bar that you see across the field of view there. And when you look at it in detail, you see that there are missing, you know, it kind of jumps. That's what I'm saying, you know, the particle just went up and down and made these holes in there, these little grooves, because in between the grooves, you can see that there's a little bit of space there where it's not very deep. So suddenly it's deep and suddenly it's not. And I'm saying that's more like a drill bit again, you know, the drill bit twirling in place. Could leave a pattern like that. Otherwise, the particle would have to jump up and down like a jumping bean in order to create that kind of pattern. And so I'm saying that what Carl Anderson found was not a particle, first of all. And if that's the case, he's got to return his Nobel medal. Okay, it was a little premature to give him one. Okay, so in summary, right? What we have here is that none of the papers that Peter gave me have particles in them. They're all done with concepts. And none of those concepts are valid in physics. And if they're not valid in physics, none of those papers are scientific. And we should all think in those terms. These are not scientific papers. They're not scientific paper because science is 150% qualitative. We don't deal with quantities. Quantities only describe. Science is about explaining. You have to explain how the magician did the trick, not what he did. You can't say, yeah, he cut the lady in half, he used 20 strokes of the saw, and he did it in 10 seconds. That describing how fast a lion runs, 30 miles per hour. Is that science? Is science saying, oh, the elephant weighed, 2 tons? Is science about saying the dog ran so much distance in so many seconds? Is that science? No, science is explaining something, explaining a mechanism. That's where you have to use your head. But measuring and say, oh, we were able to measure this to a high degree of accuracy. Like, in fact, they brought up, I think it was JFG, he brought up the issue that, Einstein's equation, one of the reasons it was successful in 1915, later on in 1919 confirmed by not Cavendish, Johnson, I forget his name now, Thompson. It wasn't even Thompson. I'm trying to get his name, but I'll get it later on. But the point is that, the fact that Einstein's equation was more accurate than Newton's, so what? What's that got to do with anything? You got to look at the explanation that Einstein gave for gravity, and that's, that you're bending space-time. That's his explanation. That's his physical interpretation. That's all we care about. We don't care about his equation. We don't care if he had a nightmare the previous night. We don't care where he got it. We care about what he comes up with and says, look, I'm going to explain to you what gravity is, what the mechanism is. Okay, what is it, Einstein? And he says, well, it's the warpage of space-time. What is space-time? Can you draw a picture of it so we know what you warped? He says, no, I cannot imagine space-time. Oh, why not? Because it's four-dimensional. Oh, so how do you know it exists? Or how do you know there is something out there called space-time? In fact, how can there possibly be something called space-time? In space is nothing. There's nothing called space. It's total vacuum. That's what space is. It's nothing. It's a synonym of nothing. And then you have time, which is obviously a concept. And you can't take nothing plus time and create a four-dimensional object. So you cannot say you warped nothing plus time. But assuming space is something, okay, so you got a rock. And we'll call that space. You got a rock. If you unite it with time, what do you have? You have rock time? A four-dimensional rock time? Is that what you warped? So it's absolute nonsense what these people are saying. They're bending concepts, unimaginable concepts, undefined concepts. And that's why, Einstein's explanation for gravity is bogus. And that's what we got to look at. Not the fact that his equation is more accurate than Newton's. Who cares about that? In fact, they use Newton every day. They don't use Einstein. The people at NASA, when they send rockets into space, they only use Newton. They never use Einstein's field equation. It's worthless for them. And let me tell you why. There's another reason for that, and why Einstein you can clean your butt with Einstein's equation. It's worthless. Einstein says, this is what his field equation says essentially. It's a point mass that's going around. See, he wanted to figure out why Mercury is perihelion. He wanted to calculate that orbit. He said, look, there's a little bit of difference between Newton's equation and what we actually observe. There's a difference there. And he says, oh, I know, I've got an equation that can explain that or justify it. And what he did, he took a totally different notion. Newton said, look, you got a mass over here, you got another mass over here. They're separated by a distance. The closer they are together, the higher the force. the farther away they are, the lower the force. In other words, distance, the greater the distance, the lower the force, and vice versa. Okay, so force and distance are inversely related. That's essentially what Newton said. Einstein says something totally different. He says, look, you take a point mass, and I can describe the itinerary of that point mass around the sun. So it's a totally different notion than two masses separated by distance. That's the difference between Newton and Einstein. So Einstein's equation is more accurate because he's talking about something else. He's talking about an itinerary of a point mass. So what? Okay, so it's more accurate. Who gives a damn? I mean, tell me why this thing, this planet, in this case Mercury, why it doesn't fly out of the solar system. So he says, I know, I can tell you that. What this equation really tells us is not really the itinerary of a point mass. It's telling you the curvature of space around the sun. It tells you the shape of the bowl. Okay? Telling you the shape of the bowl that the mass of the sun is creating around itself. That's the notion that we're talking about here. So he's telling you the shape of the bowl. And that's different than mass times mass divided by distance squared that Newton had. And so what happens when you get to that point, you say, okay, but what is this bowl? And that's where space-time comes in. And he says, well, it's space-time. It's unimaginable. We'll try to imagine it. We took space plus time. But when you look deep inside it, all they're talking about is 4 coordinates, really 4 number lines, to locate a point in space. So that's the field equation. The field equation just tells you essentially that you need 4 coordinates to locate a point within space-time. And they turned that around. They said space-time is a physical object. You bend it down and you create this bowl, and that's why Mercury has no other option but to roll around the, like the ball around the roulette. That's it. That's in a nutshell what we're talking about. Okay. Okay. So let's go on with the next topic here. The other problem we had with Peter was objects. And I started out with the golden principle. Okay. See if I can get these things up here. Here's the golden principle that I showed him. And I said, look, I want to see if you agree with this, but essentially I said I came up with the golden principle of physics, and that's like the number 1 step in physics. You need to establish some guidelines. This is the first guideline. Physics requires an object. You can't do physics without an object. And what I'm saying here is if God removes all matter from the universe, what is happening? What phenomenon is occurring? What are you watching? What are you imagining if there's nothing there? So you need an object to do physics. So what did he say? You're probably right. And that's incredible because this is not a question of probably. It's a question of yes, no. And a physicist should always say yes. And if he's got doubts about that, well, we got a big problem. I don't know what, it just gives you an idea of what he learned in college. How can he say that I'm probably right? No, I'm not probably right. You shouldn't be guessing this. You should know it. Like, there's nothing to discuss here. It's non-negotiable. It's not that I'm right. It's that you can't do physics without an object. There's nothing happening. It's just a conceptual issue. And he says you do need an object. But then again, he never, used an object in his whole discussion, in the entire debate. And not, specifically in none of the papers that he submitted. Okay, and here's a proof. Let's provide proof. Peter insinuates that the concept for the space-time is a fabric. Okay, and again, he brought that word fabric in there, which mathematical physics like to, bring into the discussion. And I'm saying there's only 3D from here to eternity or to God's heaven. There's no 2D, no 1D, no 0D or 4D. And Peter says, to that, I would disagree. So he wants to insist, because obviously, if, there is no such thing as 4D, where does that leave, all of mathematical physics, especially general relativity? If there is no such thing as 4D, there's no such thing as space-time, there's no such thing as space-time, general relativity goes down the drain. If there's no such thing as 0D, singularity, that's the end of the black holes. So there's no black holes either. And little by little, you destroy all of mathematical physics if you get rid of the 0Ds and the 4Ds, if you only stick to 3Ds. And really, physics only studies 3D, what exists. Only 3D can exist. There's no 2D, there's no 0D, no 1D, no 4D. 11D, 20, 6D, forget about all that. Okay, so what does he say? He says, well, he says the following. He says, I said, what is an object? Peter says, your point is that it has to have size. Absolutely not. That's not my point. But he continues, we don't know what the size of some particles is. Particle is a linguistic shorthand. No kidding. Particle is not a particle. It's a vibration of a field, so it's got to be a shorthand. They have to kind of hide the real notion of what a particle is because a lot of people otherwise would question it. Saying that it has shape, that's a little bit uncertain. He tells me that he agrees that we can't do things without an object. There's no physics without an object. And now he says, well, we have this particle. And he's going to say that an electron is a particle later on. He says, but he doesn't know whether it has shape. It's got size, maybe, he says. I don't know. Yeah, it could be. But he's uncertain whether it has shape. So I have no idea what he's talking about. How can a particle not have shape? And that's why he says, I'm a little uncertain. We have precision tests to determine what is the shape of the electron. We don't know yet. We don't know the electron size. Other particles are produced when we probe it. Let me tell you what the problem is. The criterion is not size, it's shape. Shape is not size, size is not shape. Size, you need another object to compare it against, okay? You can't have size unless you have a ruler. You can't have size unless you have, the elephant compared against the lion. Then you can say, yeah, one guy has a bigger size than the other. You can only talk about size if there's another object to compare it against. Could be a ruler, it could be another object, doesn't matter, but size is a comparison. That's not what shape is. Shape is, and we're not asking what is the shape of the electron. We're saying the electron had better have shape. We don't care what its shape is. Could be a blob for all we care. Could be a sphere, it could be a cube. We don't care. We're saying that if you're going to talk about an electron, if you're going to introduce it into physics, it had better have shape. That's what we're saying. We're not saying that energy has this shape or that shape. We're not saying air has this shape or that shape. We're not saying that an ocean has this shape or that shape. We're saying it had better have shape. So you can take a balloon with air in it, and that air has a spherical shape, that air. Now you put it around the earth, now that air has a shell shape. It's like a shell covering the earth. So you can have different shapes of air, but air had better have shape. If the astronaut takes a balloon into space, pops it in the middle of nowhere, that blob, if we could see it, maybe it's an irregular blob. It's not spherical, it's not shell-shaped. It's just a blob there, irregular shaped thing that's just floating in air and maybe expanding. That blob, that whole thing has shape. We don't care what shape it is. You can't say, well, it has shape here, but it's changing its shape. We don't care about that. It had better have shape. There has to be limits to that thing that's floating in space because it's made out of atoms. It had better have shape. You can't say air does not have shape. You can say that you don't know what the shape of air is inside the balloon, inside over the earth, or out there as a blob in space. You can say you don't know what the shape of air is. But air has shape. It's a yes or no type of question, not a question of which shape does it have. And the electron, same thing. We don't care what its shape is. It had better have shape if it wants to be a part of physics. And this fella says he doesn't know whether it has shape. And that we're trying to measure the size, but we can't measure the size. We don't care about all that. We don't give a damn about any of that. It's got nothing to do. It's a conceptual issue. An electron had better have shape. And it's up to the proponent to tell us what shape it has or whether it has shape. He's got to draw it. He says, for the purposes of my theory, this is the shape I'm gonna give the electron. We don't care what the real electron in the real life has. We don't care about that. And let me tell you why. If the guy's going to explain, look, how is the electron attached to the atom, to the nucleus? Well, it's hook-shaped. Then you could say, okay, I understand how the nucleus maintains the electron tied to it, faithful to it, because they're both hook-shaped, and this one is hooked up to that one. That's why the shape would be important there, because you could say, okay, I can see that. Or maybe there's an elastic, between them. And you can say, well, the electron stretches all the way to the nucleus through an elastic or a spring or a wire or whatever, a tether. And you can say, okay, now I understand why the electron doesn't fly away, because you can see the shape of it, its physical shape, because the guy drew it. He says, this is what I'm going to assume for the purpose of my theory. Fine, then you can follow his theory. But if the electron is floating out there in the middle of nowhere, and you say, what keeps it tied to the proton? What keeps it tied to the nucleus? And the guy has no answer, like Peter did not have an answer. Here were his answers. This was his, well, I'm getting ahead of myself, but no problem. Here's what he said, essentially. We had this dialogue. And he goes something like this. Let me read it here. He says, Peter, we know that there is an electron that exists at a single point in space. We know, see? He knows. You can't challenge this. There's an electron that exists at a single point. I can detect a particle in a location. So we can say with a high degree of accuracy that it is particle-like. So he's basing it on something he never saw. He just says, we see something that's particle-like, so we're going to call it a particle. Okay, but before you can tell me about that, you got to draw your atom. You got to show me how the electron fits into your atom to make sure that, it is a particle, that it can be a particle. And so what physical entity keeps the electron tied to the nucleus? That's the question. The mathematics points to photons, and those photons are considered virtual. So he's saying that photons, discrete photons, maintain the electron tied to the nucleus. By what? By magic? I mean, if I have a bunch of particles, like, balls, why would they keep a bowling ball tied to a basketball, for example? What does the fact that you have all these virtual photons in there, how does that keep another ball tied to another ball? So he has not answered the question. He has not told us the mechanism. And anyways, he introduces the virtual particle. Okay, if you want a physical interpretation, you can talk about an electromagnetic potential. Again, potential is not a physical object. Like the potential of space-time. Again, not a physical object. We can talk about a fabric which bends electrons moving forward and away from the electrons. So he's talking about a fabric. What kind of fabric is he talking about? Well, here it is. He kind of illustrated that. I think it's this one. Let's see. Well, here he showed his electron tied to the nucleus. Again, that's his notion of the atom. Okay, and again, that's the standard planetary model that has already been debunked. So the question is, what keeps the electron bound to the nucleus? And he essentially illustrates it like this on camera. He shows a ball, right? And he puts it inside a rag. He puts it inside this cloth. And he says it kind of embedded in there, and that's what keeps it there. And you can see on the right-hand side there, he drew all those lines. He's saying that's like the rag there. So I made a little better picture there so we know what he's really talking about here. He calls it the fabric. Okay, so as you can imagine, here's the rag. And you put electron beads. You can put one. You can put several eggs in there if you want in that basket, no problem. And since it's a two-dimensional type of scenario where the ball pushes the rag downwards, and that's why it's stuck out there in the periphery of the atom. I drew the little rag there on the left-hand side on the bottom picture. And you can see it, why it doesn't fall towards the center and why it doesn't fly away, because it's stuck in this depression, okay? Well, he knew that that's a two-dimensional scenario, and so he quickly changed his tune and said, well, it's more like a fluid. You got to think of it like a fluid. And to make matters worse, he added it's like an ether theory, which has also been debunked, by the way. So I said, well, what kind of rag is this? What kind of fabric is this? He says it's a potential. What do you mean a potential? Potential is a concept. He said, well, do you know what voltage is? Well, yeah, I know what voltage is. Well, it's like a voltage. Well, voltage is also a concept. And so is a space fabric and potential and rag. All these are just, words that he's using in there. Not one of them qualifies as a physical object. Especially if you're going to, a rag is a physical object, obviously, but if you're going to equate it to a potential, then it's not. And if you're going to say that you got a fabric, and you say, well, what's a fabric? What's a voltage? Well, voltage is not a physical object. Or if it's a potential, it's not a physical object. So what is he talking about? These are all concepts. So this is essentially what he's saying here. Here's another picture. He's saying you got a ball, and that ball is caught in some kind of undulation. It's you've got all these corrugated carpet, maybe, or think of it any way you want, a rag, and it's kind of stuck in there. But see, this is a two-dimensional scenario, and he realizes that. So he says, well, you really have to think about this as a fluid. So now he brings his fish tank analogy. Now you have all this fluid, all the fishies are flying around in there, right? And he puts the ball, the electron ball, in that fluid, in this three-dimensional fluid that surrounds an atom. But what's the problem is that, those fishies are not attracted to the center of the atom, neither is the ball, because a fluid has no ability to attract. So again, he has not answered the question by turning his rag into a fluid. Okay, no way that you can explain, that you can justify, that you can give me a mechanism for why the electron doesn't fly away by using either rag or fluid. And so he just keeps eluding the issue because he doesn't like to deal with these issues. He just wants to show me that the electron hit that he got on the wall or on his detector, that's a single electron hit. And he doesn't want to deal with this part, which is, what does the atom that shot that electron look like? Before you shoot the electron, show me your atom so that I can understand your atom. And of course, he doesn't want to do that. He doesn't want to deal with that. And so, we get down to what is an object? An object is that which has shape, and this is what an object is not. An object is not that which you can see. It's not that which you can touch. Not that which that has size or radius or diameter. It's not that which can move. It's not that we can measure. It's not that which has mass or volume. Not that which we can talk about, subject of a senses or is a noun. None of those. That's philosophy. And of course, it's not what something is made out of. An object is that which has shape. That's the criterion, okay, for physics and for science. And and so the devil's advocate or the skeptic, they come up and they say, okay, Bill, smart aleck, what is shape? Please define shape, because they want to go through this rigmarole where they say, well, you need words to define words and more words to define those words, and so, you'll never get to the end of it. That's their argument. That's the argument of the skeptic, of the guy who doesn't want to deal with what he calls semantics. There's a problem. The issue here is the following. We look at criteria, okay? And these are different criteria for what an object might be. Maybe you can come up with a couple more, okay? But these are the standard ones that people come up with. And I'm saying all we're doing is comparing shape against them. Are we going to use C as a criterion? Are we going to use radius as a criterion? Are we going to use volume or mass? What we're saying here is that you have all these criteria. Which one are we going to use to define what an object is for the purposes of physics. That's the issue. We don't need to know exactly what you mean by mass or what we mean by touch or what we mean by diameter. We don't need to know exactly what these words mean. All we're saying is, we're going to compare shape against them. And if you don't know the difference between mass and diameter, or between touch and subject of a sentence, well, then you got a problem, because all we need to do is compare all these and not mistake one with the other. We need to know that size is not the same thing as what you can measure. And what something is made out of is not the same thing as whether it can move. So all we're doing is choosing a criterion to define the word object for the purposes of physics. So we don't need to know exactly what shape is. We don't need to have super duper explanation for the word shape. That's the first argument. The second argument is much easier. You don't know what shape is? Very simple, because kindergartners can teach you what shape is. Go to a kindergarten, show them a block, show them a sphere made of the same material, same color, same everything, and you ask the kid, what is the difference between these two? And he'll say, the shape. He doesn't know what shape is, but he knows. Okay, that's shape. The difference between a ball and a cube, that's shape. I mean, these people just piddle around. What we need to know is what criterion we're going to use for the purposes of physics. Okay, and with that, I'm going to adjourn, and we're going to meet you again on Sunday. I'm going to continue with my criticism, because, again, this guy opened up a can of worms, Pandora's box, evil running amok through the scientific world now, and I'm going to address all that evil. I'm going to look at some of the other things that he said or weren't said that kind of puts in doubt a lot of where he's coming from. These people are really completely, they speak a different language. They're doing research in stuff that has no bearing on anything. And so these people are completely misled. They come out of college with degrees, they get a job, a teacher, or maybe in a research institution or some company doing R&D or whatever. And they don't even know, they don't have any bearings. They have no idea what they're researching, because they're doing it all based on particles. And this is simple. There are no such thing as particles, and every experiment debunks the particle and also the wave, because there's no such physical object as a wave. So wave is not even a candidate. But a particle is a candidate if it has shape. But if it doesn't have shape, it's not a candidate either, if it's a vibrating field. Okay, so we'll see you on Sunday, and we'll continue with this line of questioning. Okay, we'll see you then. Bye-bye.